Don't get sick. Please don't get sick. Crush, there should be 2 worksheets behind Lenny there. As everyone comes in, by the way, in general, if you come in after the worksheet's been handed out, I'll typically have them sitting in the back, both sides. Do we have? Are there 2 worksheets back there?
Yeah.
2 different types? There should be 2 different ones. If not, then maybe over there, here's all those cards to grab. So today, I guess before we start, one of the things I wanted to mention is that I don't know exactly how everyone's feeling on the current material and what we've worked on up to now. So unit conversions is a huge thing. That'll be on the test next week, as well as quantum with atomic orbitals and light converting between different units, that kind of thing. I've only seen a couple people in office hours. Literally, that's my job. My job is to be here to create an environment for you to succeed in class, but also to be here for you outside of class. I can't sit down for an hour with each one of you outside of class every week. That's not feasible, but that's why I have specific office hours where I check to see when I could have multiple people come. So ideally, I would have 3 or 4 people in office hours. We'd talk through problems. We'd work through solving things or concepts that you're not quite clear on. So I would really, that's what my office hours are for, and I'd love to see more people in office hours to help with anything that you're not clear on or any discussions that you want to have. If my office hours don't work for you, because I know they didn't work for everyone, I try to choose different days and times, so that if you have a Monday, Wednesday, Friday class, or a Tuesday, Thursday, then there would be a slot that would work for you. Send me an email, and ideally, if I have my ideal outside of office hours meetings during an exam week like this is to have multiple people come at the same time, so that I can get the most bang for the buck. So if you email me with a few times you're available, and a few other people do as well, then I'll try to make that work with getting a few people together so that we can use your time effectively and my time effectively, but you still get the support that you need. I'm aware that some people believe that going to office hours means that you don't know what you're doing, and it turns out there's a lot of literature. People have studied this, and it turns out the people who go to office hours are typically the people who know, who are further ahead and know that to get all the way ahead, you need to use your resources. So if you're not used to using office hours, that's one of the most effective ways to kind of get moving if you're stuck. So I hope you guys consider that as an option. For today's class, actually one thing I wanted to show you guys before we get going. I know that there's a lot that I send out through Blackboard, and the text is really small, it's not important. I wanted to make sure that you guys also know if you're trying to study for tests, there's a couple different places you can go. Where is your study guide for the test? Where is that? Where in the PowerPoints? The learning objectives. Every single day I say what it is I want you to be able to do. I try to print those out on the worksheet every day so you have them there as well, but if I forget, then they are always in the slides. I want to make sure you guys know how to navigate this to find all our course information. So course content here on the left side. By the way, if you can't find this little menu thing, you can hide that in Blackboard, so maybe you don't see it at first, but that's what I'm referring to all the time when I reference your menu bar. So content, that's where the class slides are, and all the worksheets are posted there. The other thing that might be very useful is the student reading guide. If you click on that, it takes you to a Google Sheet that I update every week on what it is that we're doing. So what's a suggested reading before Wednesday's class, before Friday's class, what's a topic we're going to be working on. And then over here on the right side, I had mentioned that set of POGL activities that we do in class. That there's a whole book with those. We can't go through all those activities. We won't go through most of them. And so here's all the extra ones that would be valuable practice for studying the material we're working on. I'm trying to decide whether I can scan a copy of that and put it in our resources folder, because I've heard that it's kind of expensive to buy if you don't buy it in bulk. Copyright issues are a little concern there. So I'll try to figure that out. If I do add that, that would be in the resources tab right here. Raise your hand if you would use that, if I put it up there as a resource. Okay, then covering the microphone. Look for that at the end of the day. It might be there. Someone else might have put it up. It might not be me. Okay. Any questions about how to use the resources in Blackboard? Study tools. Have you guys all found the practice set of problems in OWL?
No.
Like the chapter practice? Yeah.
So if you go in OWL and show all assignments, there are a whole bunch that are not for credit. The end of chapter questions for every chapter that we've worked on so far are posted to OWL. They are every single question for chapter 1, chapter 2, chapter 3. We haven't explored every part. You won't be assessed on every part. But it's like going to the end of the chapter and being like, okay, let me find some problems on the topic that I was struggling with. Let me practice them. That's a really good place to do it.
So we shouldn't be too concerned about the problems that we haven't touched.
There's like 150 problems per chapter. I just asked them to dump them all in, so it's the same thing as going to the back of each chapter and looking for problems. Not every problem is going to be relevant for you to practice. Yes?
So like a lot of that, you can't even move on to the next question until you get that right. Can you kind of skip
In those end of chapter ones?
I don't know, just don't know all the rest of them.
No, in that you should be able to skip through no problem. Yeah. All right. Any other questions that you think the class would benefit from? Post those to Blackboard discussion. I reply immediately. I think people have been going there to help answer each other's questions. It seems to be working relatively well. If you subscribe to either one of those two discussion boards, you'll be notified by email every time someone posts a question. It might be something relevant. I heard there's a lot of questions about how to answer something on the homework tonight, about how to put in like the symbol for ions, that kind of stuff. That would be a great question to post there. Put a screenshot. I can give some feedback on what it is you need to tweak in order to get that right. Okay, has everyone had a chance to answer this question? And for those of you who don't have 2 worksheets who came in a little bit later, please grab them. And I only see about a third of the name tents. If you have the name tents, please put those up. I'm still learning everyone's names. All right, talk to your neighbor. Make sure you guys have the same conclusion here, and talk about why. Worksheets are back over there by Moab and Grant. Okay, let's see what we conclude. I like how we have some interesting things, but it looks like a very large majority, basically everyone, says that this is oxygen. All right, today is another day where I'm going to say if you have not talked yet this semester, I would like to hear your voices. I'm not going to force you to talk yet. I'm starting to lean that way because we hear the same 6 or 7 voices every day in class. And that means that not everyone's being fully engaged. So please try to volunteer today and help us talk through how these things are conceptualized. So go ahead, John. How did you approach this problem?
So we know there are 8 electrons, which means there are 8 protons, and the atomic number.
How do we know there's 8 and 8? How do we know?
Because the number of protons will always equal the number of electrons unless it is an ion.
Great. And so what you were picking up on here is I said no net charge. That means it's not a cation, a positive charge. It's not an anion with a negative charge. There's no charge. So we have the same number of protons and electrons. And you said how many?
8.
So there's 8 electrons, which means if it's neutral, there's 8 protons. And so then we go to the periodic table. And then what is an element with 8 protons? Great. So oxygen, atomic number 8. That means any atom with 8 protons is oxygen. This is a neutral oxygen atom. Yes? No? We'll get there. Great question. Okay, so you have seen a couple of these. You've worked with these in your homework. I want you now to discuss with your neighbor, question number 1, I believe. What are the rules that are used to fill the atomic orbital diagrams? Talk to your neighbor, write down a list of rules, and then we'll have you shout them out, and we'll make sure that we're on the same page.
Yeah, you pair
Okay, next up. Sounds like everyone got quiet. I guess you came to consensus on what the rules are. So can I hear, let's do popcorn. I want to hear one rule from one person. We'll go around the room, try to hear as many voices as possible. This is kind of low stakes. You can volunteer what your group had to say. I'd love to hear from new voices. Can I hear some new voices? People have not talked much. Lenny, are you raising your hand, or?
Okay, I'll try.
Give me one, great.
Okay, I think we should put each of the orbital inside of the box, you know, so the arrow has to be 2 and
Okay, pause. That's great, that's one rule. So let's align on terminology. So Lenny used the term orbital. That's what we're going to call each one of these boxes. That's an orbital. And inside of that, she said we can have at most 2 arrows. What do the arrows represent? Electrons, okay? Do the arrows have a full arrow? Is it full arrow? Okay, they're all half barbed. So that's one of the terminologies we use to show electrons a lot of times. Sometimes you will see 2 arrowheads. The way I like to show it is with one half arrow. So each orbital can hold up to 2 electrons. Great. What are some other rules? We'll hear from some quiet individuals. Marlene?
Okay, before each, you have to put in one arrow facing upward per orbital before you can do the arrow going down.
Great. And I think if we're talking about like I think for our class that's a really good way to look at it. It doesn't really matter if it goes up or down, but I think your point is you have to put one by itself first before we can add 2. Can someone mention what the rule is for 2p? There's just something going on here, and we saw it for carbon the other day. Grant?
You have to fill each orbital before you can have, or at least 1 electron before you can have 2 electrons in an orbital.
Okay, I'm going to clarify that a little bit. We can only fill with 1 electron. You said at least 1. So we can only put 1 electron in each of the orbitals. If they're all the same energy, right, this is an energy axis here. If they're all on the same energy level, we have to put 1 in each before we were to go and put 2 in any one of those. Okay? What other rules? Savannah?
The 2p orbital can only hold 6 electrons. So if oxygen has 4, you would put a pair in the first and then 2 to fill up the rest, but you wouldn't pair it up because oxygen only has 4 as opposed to the 6 that 2p can hold.
Okay, and so I might tweak that a little bit to kind of meld it with what Grant said. And so if I was filling in the orbital diagram for oxygen, if we have, yellow is not useful. If we have those 3 boxes, I would say first we do 1 electron in each. The directionality of that's really less relevant, but we're kind of showing them up. And then what do we do with that 4th one? So I would say that instead of putting 2 in at first, I would say we fill everyone up with 1, and then we go back and refill afterwards. And so one of the things that I want to start talking about is the energetic consequences of doing these things. So it is energetically more expensive to put 2 electrons in 1 orbital than it is 1 electron in a single. Otherwise, we'd be pairing, and have an empty orbital there. So the energetic consequences of 2 in 1 orbital is a little bit higher than 1. All right, what are some more rules? I saw some more hands. We're missing some big rules. Any of the people who raised their hands earlier? Kayla, Love, Diana?
Start low.
Great. What does that mean? What is low on this axis, on this graph? Great. So we start with the lowest energy, the most stable orbitals first, and we fill upwards. I think everyone assumed that, but we need to specify it because if we only have 1 electron, we can't put the 1 electron up in 2s. That's not the most stable configuration. And remember, if we're thinking about Bohr's model, the atom is kind of a little bit of a guide. I know that that's not accurate because the electrons don't go round in an orbit. But but this is closest to the nucleus. The 1s is the smallest, the probability is closest to the nucleus, which is most stable, and that's where we're going to find electrons first. Additional rules. That was one of the biggest ones. Aaron?
When you're going to fill an orbital, when you get to electron pairs, the second pair has the opposite spin.
The second electron of a pair has the opposite spin. Great. And so it doesn't really matter if we have one electron by itself, whether it's up or down. That's a little bit less relevant. But, like Aaron said, when we add the second electron, it has to have the opposite spin. And we denote that by having the opposite direction that the arrow is pointing. Very good. Are there more? Christina?
You have to build a full level before you can go on to the next level.
Fantastic. Talking about starting with the most stable ones first, we have to fill every orbital in the order that they're shown here before we can move to the next one. And how many electrons does it take to fill one of these orbitals? 2 electrons, opposite spin. Kayla?
I'll say Heinz rule for orbital diagram.
Okay, what does that mean?
It said that the most stable arrangement of electrons in a stellar shell is that with the maximum number of unpaired electrons all with the same spinning direction.
Okay, so talking about if we can, we put all of these in the same direction before we double them up. So 1 electron in each. It's kind of Hund's rule. And then we also have to, once we have half full orbitals, then we can go ahead and fill them up. And then we move to the next one. You guys ready to start filling out some of your own? You've already done some of this in your homework, but hopefully when we're talking about the rules and we're describing it, hopefully it'll be much more clear at the end of the day how that relates to ions, how that allows us to predict a whole bunch of things about the atom. Quantum really is the defining set of rules that allows us to think about bonding and molecular shape and everything else. So that's why we're spending a lot of time on it. All right. I think these are some of the rules that I wrote down. I think we got to all these. Start at the bottom, fill at the lowest energy first, go up to higher energy. Each orbital can only hold 2 electrons, their opposite spin. Spin is denoted by the direction I'm pointing. And we're going to be using this term degenerate. Has anyone ever been called degenerate before? I'm not going to get into that story. So degenerate in chemistry means something different. Degenerate means that they're all the same, all equal energy. Are 1s and 2s degenerate?
No.
They're not the same energy, so they're not degenerate. What about 2p, x, y, and z? These 3 all have the same energy. Honestly, we usually fill from the left to the right. It's irrelevant. We could fill from the right to the left. They're all equal energy levels. The point is that if we're putting 4 electrons in or 3 electrons, we fill 1 electron in each first, half fill those orbitals before we come back a second time. So by the end of today's class, you will be able to write electron configurations, the full and condensed, using atomic orbital diagrams as a tool to do that and to visualize what those configurations mean. That's going to allow us to determine the number of valence electrons that are available for bonding. Kayla?
I have a question about that. I asked Matthew yesterday, Monday, in the book, when they're writing the electron configuration, sometimes, most of the time they put, like, say you go all the way to 3D and then you go to 4P. Sometimes they'll put the 3D
Yep.
before the 4S, and the 3. Do we have to write it that way, or do we? Or can we
Yes.
write it the other way?
You mean like what order they're written or what order they're filled?
They're written.
So if we see it like this, one of the things you're pointing out is that 4s is actually lower energy than 3D. So we don't fill all of 3 first before we go to 4.
No, I mean like just when we're writing.
And so when we're writing that out, what does your book do? Does it write 3p, 4s, 3d? Or does it write 3d before 4s?
It writes 3D before 4S. And you've been on the homework sometimes.
Yeah, that's why I was
Does it give you wrong if you do
He does it.
No, it doesn't.
4d before, or 4s before 3d? Yeah, so I don't have a preference. In my mind, it's a lot easier to write it in this order because this is the order that I fill it in, and that shows you the different energy levels that go forward. We'll get to, I think, some questions regarding that, and so we'll kind of show both ways, but I don't have a preference. And the major thing I want you to be able to do with quantum, with the application of atomic orbital diagrams, is to justify a whole bunch of trends that come from looking at the periodic table. Some of the things you're doing in your homework is what charge are we likely to find? A lot of that comes from some of the descriptions we'll be looking at today. What's the atomic radius of an atom? What's the ionic radius? If it has an extra or 1 minus electron compared to neutral, what does that mean about the radius? Ionization energy. How much energy does it take to remove an electron from a particular element? And this is something we might get into more on Friday, but these are all the trends that I think electron affinity is one more, talking about how likely is an atom to, what are the energetic consequences of accepting an electron. So we'll spend some time with each one of these. I think we'll get through atomic and ionic radius today, and then we'll spend on Friday some time on these last two. So let's go ahead and answer this question. You can do it however you want. Once you have determined the answer yourself, then you can check with your neighbor if they're done as well. And you're welcome to use the atomic orbital diagram. You can use one of these right now if you want, if that'll help you. You have 4 to use for today. Alright, looks like we have almost everyone submitted. Have you checked with your neighbor? Can I hear from a new voice? How did you answer this? What's the approach? Yeah, go ahead. Remind me your name?
Gail.
Gail.
Well, in the homework deal with the chart, it says that you can go with like 1S level and then 2S, 2D, and then 3S, 3P. But that's how I was looking at it. I know that's 3P, so it's 1, 2, 3, 4, 5.
Great. So one of the really valuable approaches is to think about how things are laid on the periodic table. The first 2 rows here, first 2 groups. What do we call that block? This is the S block. So that means whenever we're filling this, we're actually filling in S orbital. This center part here, the transition metals, what do we call that? D block. And on the far right, these groups are the P block. And so you could really easily do it, Gail was saying. You can see that we're talking about chlorine. So we have 1, 2, 3, 4, 5 P electrons, or electrons in the P orbital. We can say, well, what P orbital is that? Well, it's 1, 2, 3 rows down. So it's in period 3, so that means those are 3 P electrons. And so we have 5 of those. What if I asked you how many 2 P electrons does chlorine have? Talk to your neighbor. How many 2 P electrons does chlorine have? Okay, we heard that resonate around the classroom. 6, how do we know that?
It's completely filled.
Great, so going back to our rules, we fill electrons from the lowest energy to the highest energy. So why don't you go ahead, if you haven't already done so, fill out the atomic orbital diagram for chlorine. Use one of your 4 to do that. Make sure that you compare with your neighbor and you're using the same rules. Everything looks the same. It's not a fucking question. A couple more seconds to complete your diagram. Make sure to compare it to your neighbor. All right, so how do we do this? Someone talk me through. Jason, you want to talk me through? Is that you raising your hand?
I'll go ahead. Good 3p has 5 in it, so you have, in 3p you have 2 in the first orbital, 2 in the second orbital, and then 1 in the third orbital, which means every one under that has to have at least 2 electrons in each orbital.
Okay, so one way to do it is we know where chlorine is. We know it's in 3p, has 5 electrons. We kind of backfill from there. Totally legit. Did anyone do it the other way around, starting at the bottom, working their way up? Joey?
You can figure out what how many electrons it has and literally start at the bottom and fill in all the blocks.
Fantastic. And I think that might be sometimes a safer way to do it in case you mess up which subshell you're filling at the end. Because if you accidentally said it's 4s or 4p instead of 3p, then you might fill way too many electrons, so you need to make sure the numbers line up. So how many electrons do we have for chlorine? If it's neutral, 17. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then there's 7 more that we already have in 3p, so that lines up. Both of those approaches will work. True, I zoomed in. There are 5 electrons in 3p, so I totally was wrong when I made that statement. I can count. Just so you guys know, I was zoomed in, so I couldn't. Minus 4 points. Okay. So this is one way of doing it. I want to take a look for a second and deconstruct this atomic orbital diagram. If we had helium, what orbitals would be filled? Talk to your neighbor. If we had helium, what orbitals would be filled with electrons? Okay. Caleb, which orbitals would be filled if we had helium?
Just 1s.
With 2 electrons. We'll call that a duet. What about neon? Amber?
2s and 2p.
And 2s, 2p, and everything below this would be filled for neon. What if we had argon? What would be filled if we had argon? Dawson?
1s, 2s, 2p, 3s, 3p.
Zooming in too far. What trends are you seeing? Okay, so talk to your neighbor. Why am I highlighting noble gases? What's special about them as they're laid out here? Go talk to neighbors. Why are we highlighting noble gases? So can I hear from a new voice? Why am I highlighting noble gases here? Gail?
Well, it's easy to remember when you're doing like shorthand configuration. You know that AR has 18, so you do AR. It makes it easier. It's like,
Okay, so there's some reference to the noble gases. I want to clarify a little bit what that means and looks like. Mode?
by filling each p orbital, you end up with the same amount of electrons as one of the noble gases.
Great, so one of the major things is when we're writing shorthand or condensed configuration, we're going to be referencing the noble gases. So that's useful for helping us write less and still have the same information conveyed. We'll be getting to that one more second. What else?
The last orbital for all the noble gases coming down.
Great. So if we're looking at this, remember stability is one of the things I want us thinking about. And so what Tripty's pointing out is that if we're talking about chlorine, it's not necessarily as relevant yet to be talking about argon's noble gas configuration. But neon electron configuration is full, and then we have 7 electrons past that. Where does that number 7 stand out for chlorine? Say again? That's how many valence electrons chlorine has. What are valence electrons? They're the outermost shell of.
The electrons of the outermost shell that can be used for bonding.
They're the electrons that can be used for bonding. What is special about the noble gases?
They don't, they have 8 valence electrons, so they're already full, can't do anything.
So, combining what Bria and Jackson said, because they have 8 or 2, that's just why I said duet, right? Helium only has 2 electrons. This is a full shell. That full shell has an increased stability. That means that those electrons are most likely not going to react. We're not going to count them in the outermost shell because they're not available for any reaction. We're going to be talking a lot in chemistry about why things react, and the reason they react is because they have electrons that are outside of the core stable electrons. So I want us always thinking about where is this electron configuration compared to a noble gas. And we'll do some practicing of that. So go ahead and write the full electron configuration and the noble gas configuration for chlorine. Full electron configuration, just so we're on the same page, 1s2, and you can kind of write all that out. And then the condensed is it has a noble gas configuration, and then it has some more than that. If you've already done it for chlorine, there's a couple more elements below that you're welcome to start trying. Is it thick though? A thick one? Cool. If you don't mind throwing it up so everyone his hands over here. Okay. I'm guessing that most people have done this for chlorine. So can I have a new volunteer, a new voice who has not spoken yet in class today, volunteer to read the full electron configuration for chlorine? Lauren? Yes, please. Great. Why did I put square brackets around part of that configuration? Taylor? Yeah, you're on the right track.
Neon, so then when you do that, that tells you it's got the neon, you don't have to absolutely write that, you can just put that in the bracket.
So we know that this is the highest occupied set of atomic orbitals, but we know that there are 2 noble gas configurations within that. And so what we're doing is we're putting square brackets around that configuration. We could also put square brackets around 1s just to kind of like help. I do that sometimes to help me picture where the noble gas configurations are, where those stable electrons are. And so here the stable electrons are 1s2, 2s2, 2p6. So what is the condensed electron configuration then? How do we write that? Angel?
Ne in brackets 3s2, 3p6.
3p. Great. Okay, so it's a shorthand way of saying, well, I have all of these electrons, but that's neon's electron configuration. Does that mean that we have a neon atom inside of our chlorine atom? Okay, so careful. We're talking about electron configurations. That doesn't define the element. We need to make very clear we don't mix those two up. So we have electron configuration of neon. That is stable. We have 7 additional electrons that are outside of that. How many valence electrons do we have again? 7. All of these electrons here are valence electrons. Those are the ones we're going to focus on when we talk about reactivity of the atom. So there's a number of different reasons we're doing this, but I want us to be able to write both the full electron configuration and the condensed. When you write the full, do you have to write the square brackets? No, that's just something I do to help me see what the condensed configuration will be. It's not wrong. It's just not necessary. So go ahead and think about Our next question, how many electrons would chlorine need to lose or gain in order to be isoelectronic to the nearest noble gas? Talk to your neighbor if you're not quite sure how to answer this question, and then click in your answer. Plus is positive, so there's no plus, I think, in the system. Yeah, so just the number. So if it's positive, you would just do the number, because those are positive numbers. If it's losing, then you would have minus. A couple more seconds. All right. We have a vast majority of the class responding 1. So plus 1. What does that mean? How do we choose that answer? Can I hear from a new voice? New voices, new voices, new voices, new voices, please. Come on, someone, if you haven't raised your hand today, haven't spoke out today, please share. Look.
So I said it would gain an electron, meaning that it would fill that 3p all the way up, meaning that it would become argon.
It would become argon?
No, it has the electron configuration of argon.
Thank you for pointing out a common mistake in the wording that we use, and correcting yourself without even any discussion from my side. So if we have this electron configuration and we gain 1 electron, what's the condensed configuration going to be? So let me do it 2 ways. I'm going to do this first, 3s2, we're adding 1 electron, 3p6. But we said before that if you fill 3p6, that is argon's configuration. And so chlorine, if you gain an electron, Cl minus, its electron configuration is argon. Argon's electron configuration. Square brackets. Is that going to answer your question, Kiana? Well, one of the questions. Okay, why is it relevant? I guess we'll work through that kind of as we go. So go ahead and do the same thing for calcium now. I think that's requested to have the full and condensed electron configuration. And then think about how many electrons it would lose or gain to be isoelectronic to the nearest noble gas. Did everyone figure out what isoelectronic meant, by the way? Can I get a definition for isoelectronic? Kayla?
Isoelectronic elements have the same number of electrons but different number of protons.
Great. So iso means the same. Electronic is the electron configuration. Isoelectronic means that Cl minus is isoelectronic to argon. They have the same electron, same number of electrons, and hence the same electron configuration. Great. So go ahead and work through calcium. Raise your hand if you need any questions. I would ask that you also fill out the atomic orbital diagram to visualize it as well as do the numbers. And then Sam and I will be walking around if you need any help. If you finish, I think there's another element. Sulfur is the next set of questions. You can fill out another orbital diagram for that if you want. I would trust it. Ask it first. Your biggest mistake is trusting. I'd like to volunteer to draw their orbital diagrams of calcium.
Calcium has how many?
Don't be too careful.
Oh, okay. Where's calcium? 20? Look at you go. My handwriting sucks. It's okay. You just gotta fill them out for us too. Really, you could just put 2 dots in both of them and it'd mean the same thing.
I think the first question is sulfur, and then it asks about.
Well, it asks about the sharing.
There we go.
Yeah, so fill it out for sulfur and then see how many electrons you would gain or lose.
Okay.
All right, so we have Love's drawing up here for the calcium atom. If it's neutral, how do I know calcium's neutral in this? Okay, remember, so if we don't see any symbol for a charge up there in the top right corner of the symbol, the elemental symbol, we assume it's a neutral charge. So if on an assessment I were to give you CAA+, then you would draw that out according to it would have 1 less electron than would be the number of protons. Okay, so Love drew this. Do you want to say out loud what the full configuration is? Great. Anyone have a question about how we got there? So what's the condensed electron configuration then? Okay, so the configuration up to here is argon's electron configuration. Those electrons are stable, they're not going to be touched, they're in the core of that element. We'll talk about how that doesn't always happen. When we say stable, it's relative to everything else. You can get at those electrons, but it would cost you a lot of energy to get at those electrons. Okay, so if we were to find calcium as an ion, how many electrons would calcium need to lose or gain in order to be isoelectronic with the nearest noble gas? Go ahead and click in your responses. A couple more seconds. Closing out. Is it gaining 2 or losing 2? Which 2 electrons is it going to lose? 4s1 and 4s2. So if we go out in nature and we find calcium, we're most likely to find it in the +2 state. Is that just true for calcium? Are there other elements that follow that same trend?
Like magnesium?
Why magnesium? Okay, so a lot of times in chemistry they'll teach like what charges you expect for what elements before quantum, and I don't like to do that. I like to do it the other way around. I like to think about why. And so if we look at anything on this periodic table that's in the S block, if it's in the first group, group 1 on the periodic table, that means it has 1 electron in an s orbital. If it loses that electron, it's going to become isoelectronic with the noble gas configuration before that. If it is in group 2, it means it's going to most likely lose 2 electrons to be isoelectronic with the nearest noble gas. Over on the other side, if we're in group 7 with chlorine, how many electrons are we likely to lose or gain again? Gain 1 electron to be isoelectronic with the nearest noble gas. So if we find chlorine with an ion, it's going to be -1. Is that true for sulfur as well? No. What else is it true for, though?
Gain 2.
What's chlorine's trend going to be similar to? What other elements?
Chlorine.
Chlorine, bromine, iodine,
Acetylene.
Yes.
You say
Yeah,
that
you
word.
do that.
And one thing I want you to notice, do you notice where helium is on this periodic table?
Yes.
What's different about helium on this periodic table from other ones you might have seen?
Hydrogen?
Yeah, sorry, hydrogen.
I'm gonna say
Hydrogen.
over there.
Matthew?
Well,
It's usually only on the left side, but this one has it over on the far left and in the...
So it's in group 1 because it only has one 1s electron. But they also show it in group 7. Why is it in group 7? It can gain one electron to be isoelectronic with helium. So it's a way of kind of categorizing that you might not often see, but I really like. Okay, and the condensed electron configuration from calcium-2+. Can anyone shout that out? Talking about calcium-2+, what's a condensed electron configuration? Argon in square brackets, because it has the same electron configuration as argon. You starting to get the idea of how this all fits together? And starting to think about how we can make predictions about the charges we're going to find on different elements. So we just mentioned sulfur. I don't think we need to go through the whole process of this. I saw a number of people already working on this. Sulfur is in which, well, so can anyone tell me what group sulfur is in, and hence how many electrons it's likely to gain or lose in order to be isoelectronic with nearest noble gas? Caleb? Group 6, and 6A means main group 6, so sometimes we just say group 6. So it's in group 6, so how many electrons is it likely to lose or gain to be isoelectronic? Can gain or share 2. So that's why I put share in here. And then it will be isoelectronic with? Argon. All right? And so we can do this for a lot of different elements. Once we start getting into the nonmetals, the nonmetals is this big chunk right here that's above the red line. Those ones are typically not going to be found, a lot of them are not going to be found as ions, especially on the far left side. You're not going to find carbon as a 4- ion or 4+. It's going to be sharing electrons instead of stealing them. And we'll be talking about that throughout the next week, talking about how they can share electrons and what that means for stability. So if you haven't already, you can do sulfur on your own. I want to talk for the last couple of minutes that we have in class about atomic trends. And two different things. I want to look at, if you look at the trends of the periodic table, I've cut out the center part of the periodic table, which Bria was asking me about earlier. The transition metals, because I'm focusing on the main groups, 1, 2, 3, 4, 5, 6, 7, 8. That doesn't include the transition metals because they have a little bit different ways that we interact with them. But if we can identify how many electrons passed the previous noble gas, this term valence electrons that we use, we're really going to be focusing on how many s and p electrons there are. Some of these elements will also have d electrons, and I don't want to worry about those so much for right now. But the d electrons are the ones that are occupied by the transition metals, and those electrons are typically not referred to as valence electrons because of the way that they interact with other atoms. If you look at the periodic table, we talked about the s block, the d block, and the p block. One of the things you might not have thought about before is this block at the bottom. Why is this block here at the bottom of the periodic table? Matthew?
Because if it was in the middle, it would be ridiculous.
So if it was an accurate periodic table, it should actually look like this. We have the F block, but the F block is kind of taken out to make it fit on a regular sheet of paper. So this is the full periodic table. That part at the bottom is just kind of like inserted. Should be inserted on the periodic table. So let's do one question. I think instead of doing this one question right now, because it is a little bit of a complicated question, we're going to say that the learning objectives for today, we got through the first one here. Charge if found as an ion. We'll be working on atomic radius, ionization energy, electron affinity in class on Friday. What do you have to do today? Homework, post-quiz are both due today. Hopefully you've been working on those throughout the time until now. If you can't work in groups, you can email me. Maybe there's some time. I think at 2:30 I'm meeting with some students. If you want to meet with me then, send me an email. There was a quick class assignment before class today. They're doing 9 a.m.
Is the stuff you know for Friday also?
I've got an hour after this last one, I have to go.
Everything up to the structures. So this stuff.
Hey, how you doing? My name's Jeff.
Hey Jeff, what's going on, Mark?
I'm good. Next semester I'm taking general chemistry.
Okay.
Is that the class you're teaching right now?
This is.
Yeah, like this style. What's your name?
My name's Mark Bailey.
Okay.
But I will be teaching a night class next semester, and it's CHEM1402. And I only teach one section because I'm doing a research program as well.
Oh, okay.
So if you're free during this period, you're always welcome to come join us this semester, but I won't be available
Even
this
though I'm not
semester.
registered for this? Okay, I'll start doing that.
Yeah, the only,
Like I said, I'm starting to tune it
I'm
out.
trying to think, if you wanted to participate in the class as well, we use iClickers, and it's $15 to actually get on the thing, or you can just sit and talk to people. It depends if you actually feel like you're submitting something and getting feedback. The thing that you can do is like zoom in on the slides when I submit a question. So you're welcome to just sit in. I ask you not to sit in the very back. If you're going to come join us, join us. Sit in the class.
Got it.
Say your name again?
Jeff Alexander.
Cool. Very nice to meet you.
Thank you.
Yeah, what's up?